Let me start recording. So welcome to the last meeting of our seminar in this season. And today our guest is Anand Sawant from the Tata Institute, who will speak about central extensions of algebraic groups via cellular A1 homology.
Thank you very much, Muna, for this invitation. And yeah, I'm really happy to speak in this electronic algebraic K theory seminar. So, of course, this is joint work with Fabien Morel. And I see that some of you in the audience have seen me talk about this in some form, but I hope you'll find something new. Yeah, so okay, so let's just get right into it. So I'll always work over a perfect field K, and by HK, I will denote the unstable A1 homotopy category constructed by uh, Morel and Wobodsky. So, by the way, it goes without saying that, I mean, feel free to stop me at any point in case you want me to clarify something. So, as we all know, so the objects of this category are simplicial sheaves of sets for the Nisnevich topology on the category of smooth schemes on K. Uh, okay, so this is about central extensions. So let me, uh, yeah, get to the objects that I want to study. So let for now G be a sheaf of groups in this category. Uh, so okay, it's always Nisnevich topology, but sometimes I will not mention it. And let M be a sheaf of abelian groups. Again, a sheaf of Nisnevich sets, Nisnevich sheaf of sets on smooth schemes, and so very soon M is going to be what is called strictly A1 invariant. So I'm not putting this assumption right now, but anyway, so I will let me introduce this notation. So app A1K. By this, I will denote the abelian category of strictly A1 invariant sheaves. And by this, so a sheaf of abelian groups is in app A1K if and only if you look at the Nisnevich cohomology pre-sheaves with coefficients in M, so then these are A1 invariant for all I. Okay, so it's a highly non-trivial fact that this is actually an abelian category. So I mean this is I mean I'm not going to do this in detail, but this is done by obtaining this category as the heart of a particular tree structure. Uh, okay, so I'm interested in this group, the group of central extensions, isomorphism classes of central extensions of G by M. So yeah, so the set of iso classes of central extensions of G by M as Nisnevich sheaves of groups. And yeah, so of course this means exact sequences of this form of sheaves where M is contained in the center of E. But anyway, I'll not write this down in detail. And of course, this forms a group under the operation of Bayer sum. Okay, so let me quickly mention some formal results about this group. So let me just call this abstract nonsense. This just says that this group is just the ext2 in the category of sheaves of abelian groups with a G action. Okay, so when I write app k, it's just the category of sheaves of abelian groups on smooth schemes. And yeah, so when I put an A1, they're strictly ever invariant with CM. And this can also be identified with H2 of BG with coefficients in. Okay, so this is essentially formal, works over any topos, but we'll just take this for granted. So here's the theorem. Okay, so if so now I come to certain hypotheses. I'm not going to explain them right now, but yeah, I mean, because I will not be using the explicit definitions. If G is A1 connected, so to any space you can associate its sheaf of A1 connected components. You just say that that sheaf is trivial. Or equivalently, you can say that its sections over any finitely generated separable field extension of the base field are trivial. I mean, trivial, by trivial, I mean one point set. So if G is A1 connected and M is strictly A1 invariant, then the canonical map. So I'll tell you how the canonical map comes about. So there's a canonical map from this group of central extensions to M torsos on G. This is an isomorphism. So this part is essentially formal. I'll indicate a proof shortly, but the non-trivial part of the theorem is the next one. So moreover, so you can yeah, now specialize G to an algebraic group. So if G is split, so don't worry about the decorations. So I'll just indicate whether required. So split, semi-simple, almost simple, simply
I have a
connected.
simple question.
Yeah, sure. Yeah,
G
sure.
is a sheaf of sets, and yet you're talking about G is a smooth scheme in your
Yes,
theorem.
yes. Yes. So I mean, the right hand side needs to be appropriately defined as yeah, as uh, I mean, you can use that. You can assume that the Eilenberg-Maclaurin spaces exist, and then you can make sense of the right-hand side. But yeah, I kind of shoved that under the carpet. But yeah, I mean, well, I mean, it for all practical purposes, it is enough to assume that G. I mean, there is an underlying scheme G. So all the applications are exactly in this setup. So yeah, so simply connected algebraic group. Does that answer the question, by the way?
Yes, it does.
Thanks. Okay, then you can compute this right-hand side. As follows. So I'm going to write a formula and then explain it later. So m minus 2 of k. So depending upon the type of G. So if G is of symplectic type, and eta torsion in the m minus 2 of k otherwise. Okay, so now this minus 1 is the contraction functor. I believe it was first defined by Wygotsky. And so you just apply it twice. And so this eta is the object corresponding to, is the element corresponding to the Hopf map in A1 homotopy theory. And one can show that whenever you contract a strictly abelian sheaf, it has an action of eta. And you take all the elements which go to 0 after multiplying by eta. Or after the eta action, and so that's what this group is, and I'll indicate where this. So actually, this is the meat of the theorem, this second statement, and that's what I'm going to mainly focus on. But let me just mention that when so when M is Milnor K2, this is due to Brylinski and Deligne. And when M is a cycle module in the sense of Frost, this is due to NO, Kahn, Levine, and Feweg. And when M is the unramified Witt groups, the sheaf of unramified Witt ring, this is due to Stefan Giller. So anyway, yeah, so I'm going to quickly give a sketch of a sketch of the proof of this theorem that I stated. So the first part of it is quite formal, at least from the point of view of topologists. And yeah, so then I'll come to cellular even homology, which allows us to address this part, this explicit computation. So of course, this -2 over here and this eta has something to do with the Milnor Witt K2 and Milnor K2, and this eta torsion comes from the fact that Milnor K2 is Milnor Witt K2 modulo eta. But anyway, I will come to this later. Okay, so let me give a brief sketch of proof. Okay, so what one does is consider the skeletal filtration on BG. So this is a simplicial classifying space on G, and so let me denote it by F dot. And this comes with co-fiber sequences of the following form. So if you take the inclusion of n-1 skeleton into the nth one, then the co-fiber is the n-fold suspension of G smash n. Okay, so yeah, I mean, this is kind of formal. So, but for the reasons of connectivity, I mean, of course, this sigma n of the n suspension of G smash n is n connected. So if the original thing is zero connected, of course. So for connectivity reasons, so this is the group that we are interested in computing. So the second cohomology of BG with coefficients in M. So this is just the homotopy classes of maps from BG to KM2, and this will be F3 maps from F3 BG to KM2. So of course I'm being slightly vague for the reasons of time about where you are taking these even homotopy classes. So it doesn't matter if you take it in simplicial homotopy category or the even homotopy category. That's because since M is strictly A1 invariant, the Eilenberg-Maclaurin space is A1 local, and so these two are in bijection. Okay, so now what one can do is apply, so look at this part of the co-fiber sequence, F2 to F3. And apply homotopy classes of maps into KM2 to get an exact sequence of this form. Okay, so let me just write this out. So now clearly the leftmost term is 0 because we are suspending 3 times, and it's just KM2. Okay, and this is sigma. So now there is one suspension less. So as I said, this is 0. And yeah, so you can cancel this with this 2, and then you have, so then this is just what I'm going to write, m tilde of g wedge 3. So what is this? So okay, in general, so for any pointed, so right, a, so I so m of a will split as m of point direct something, and that something I'll call the reduced yeah, part of m of a. So that is what this is. Okay, so I'll come to this in a moment. So you can do the similar analysis for the for the cofiber sequence at one level down to this one. So f1 bg to f2 bg to sigma 2 of g smash 2. So note that this is just sigma g, the suspension of g. And in that case, so you will get, so start with sigma 2 g smash 2 maps into km2. And this will be m tilde of g smash 2. Then homotopy classes of maps from f2 pg to km2. Then sigma g to km2. Okay, so this is the part that we are interested in at the end over here. Okay, so we are, I mean, okay, so this is the group that we are actually interested in. This is the our central extensions of g by m. And so we need to understand this guy. So this guy is understood as the in terms of this guy and the kernel of this guy. But what is this right hand vertical map? So this is nothing but h1 nis gm, because you cancel, so it's just maps from g to km1. And this one over here is h1. So of course now h1 has to be appropriately defined because g smash g is not a scheme, it's a space. But yeah, you can define it as maps into km1, and then you have it. And
excuse
okay.
me, let me ask why this on the top f3 bg to km2 is the central extension at the matter with this?
You mean this one?
Yeah.
Oh, that's because of this over here. So because of connectivity, so I mean, if you want to calculate this one, then it's enough to calculate from here, because I mean, if you look at the cofiber sequences, the co-kernels will be of very highly connected, more than 3 connected.
Okay, thank you.
I mean, so maps into km2 will not matter for n greater than or equal to greater than 3. That's why. So now, and of course, if one goes through I mean, really how this map is defined, one can check that this is just induced by, so this map is induced by PR, I mean, the sum of two projections minus the product. So this is exactly the map coming from the simplicial structure of PG. So this is something that one can check. Okay, so now what these two exact sequences that I have drawn. So this is what we want to understand. And so if this guy on the right vanishes, then these two will be equal. And if this guy and this guy both vanish, then these two will be equal, and then we'll have our answer. Okay, so just to summarize, yeah, so this above exact sequences imply that so if m tilde of g smash 2 and m tilde of g smash 3 are 0, then So there exists an exact sequence of this form. So and of course, I mean, if this guy on the right is 0, then we have our answer. And now why does this happen? So now so note that we haven't really strongly used that M is strictly even invariant. I mean, of course, we used it while writing this homotopy classes of maps, and we wanted to come from the A1 homotopy category to simplicial homotopy category. So that's where we use it very strongly, but we'll use it once more. So this time we'll only use the A1 invariance of M. So M is A1 invariant. So this implies that so for any x, M of x is just Hom of I mean in sheaves of I mean sheaves on smooth schemes from pi naught A1 x to M. So I mean, in other words, any morphism from x to M factors through pi naught A1 of x just by the universal property, because M is A1 invariant. And so for x pointed, you have the similar thing in terms of pointed maps of pointed sheaves of sets. And now, so the point is that if G is as in the theorem, that means if you put all those assumptions, that split, semi-simple, almost simple, and simply connected. So examples are like SL2 or SLN or the symplectic groups and so on. Then in that case, so G as in the theorem implies that G is even connected. And that just means that these two guys are 0. So then we have an exact sequence like this. But moreover, this guy also will be 0, because if G is even connected, then its suspension with itself will at least be 1 connected. So the connectivity, I mean, of the suspension is 1 more than the connectivity of 2 spaces. So then this guy will also vanish, and then you would have the first part of the theorem. Okay, so this implies that M2 and M tilde G smash 3 is 0, and yeah, so H1 is M is 0. So then we are done. So then this gives the first part of the theorem. So now all that remains is to actually compute this one. So again, for the reasons of connectivity of G, so this can be written as Hom in the category of strictly even in the abelian category of strictly even invariant sheaves from pi 1 into M. And so in fact, so this theorem boils down to yeah, so we are reduced to computing the pi 1 A1 of G. And yeah, so this is the main this is the main topic of today's talk. So this is K2 Milnor weight or K2 Milnor, depending upon whether G is of symplectic type or not. Okay, so I mean, anyway, so the reason for I mean, anyway, so this kind of shows that well, anyway, I'll give a more precise version of this theorem, let's say hopefully 10 minutes from now, and I mean, then it will be kind of clear that so these kind of reasons have I mean well, I mean, what this says is that this is completely dependent on it's dependent only on the type of G. It's not really, it's kind of independent of the group. And yeah, so that is somewhat striking. And of course, I mean, the experts would have noticed that if you evaluate these things, I mean, these are basically the sheafy versions of the classical results of Matsumoto. Okay, so I'll now so now we are going to switch tracks and we are going to focus our attention on computing pi1. Are there any questions?
Is this pi1 group sheafified?
No, I'm sorry, I didn't get the question. So it is a sheaf of groups. Was that the question?
Yes, it was, yes.
Yeah, so it is a sheaf of groups, and in fact, it's a sheaf of abelian groups, because I mean, you are taking, you are evaluating pi1 of a sheaf of groups. Okay, so anyway, so since that has come up, and since G with all the hypotheses that we have written down is A1 connected, this just means, oops, this just means that the A1 fundamental group agrees with the first A1 homology group. But as we all know, so this group is quite uncomputable. That's because I mean, so the definition actually involves the so-called A1 fibrant replacement functor in A1 homotopy theory, and the description of which is not at all explicit. I mean, it's not at all computable. There is an explicit description, but it's absolutely useless for any kind of computations. So anyway, so one has to find some other tricks to do this. So I have given this talk maybe 2 or 3 times before, and so every time I realize that if I try, so of course there is a natural, so there is a natural filtration on G, and the most obvious way of computing this kind of homology group is to write down the spectral sequence for the filtration and then compute using it. Assume that, I mean, you just hope that the strata of the filtration are nice enough, and then you can write down, and you can expect some sort of degenerations, and then you can write it down. And the way to do this is very much parallel to topology, in which the way we define cellular homology and show that cellular homology is equal to singular homology. So we are not so lucky here. So the cellular A1 homology does not actually agree with A1 homology in all degrees. Only the first non-trivial one agrees. But I'm not going to spend time in giving explicit definitions of cellular A1 homology, precise definitions of the cellular A1 homology. But what I will do is I will, since I want to say something about some of the ingredients of the proof, so I'm going to focus on the explicit structure of the stratification that we have, and yeah, directly make computations through it, and then hopefully that will clarify what the definitions are. But anyway, so now our G is it is assumed to be an algebraic group. It's assumed to be split, semi-simple, simply connected, and almost simple. So I'm going to change tracks and now go to a bit of algebraic groups theory. So when one so the cellular structure on G is given by the Bruha decomposition, but in order to nail everything down, we need to fix some data. So that data goes by the name of pinning of G. So this consists of, so G is split, so it consists of a maximal K-split torus T and a Borel subgroup D containing T. So okay, so exact definitions are not really necessary at this point. Only, I mean, I'll point out what is required, what is really required. So what these two do is, so these groups are determined by their so-called root systems. So they determine a basis of simple roots. And of course, the pinning also involves fixing an isomorphism between the so-called root groups and GA. So this is the additive group with the so-called root groups. So anyway, I mean, those who are not familiar with the algebraic groups theory, they need not, bother too much about this thing. So only thing that you need to remember is that there are certain special A1s. So this is actually, as a scheme, it's just an A1. There are certain A1s which has a nice action of a torus in terms of this root, in the sense that so this root actually is a character of T, and so one has a kind of relation of this form. So the conjugation action of T on U, so for any U in this U alpha, is by the character, something like this. So so there are some natural A1s which are in the group, but what one needs to do is spin an isomorphism. Okay, anyway, so I'll probably not get into technicalities regarding this, but I'll just indicate where these are going to come into picture. So the next thing that we are going to need is the while group of G. So this is the normalizer of the torus inside G modulo T. And this is a finite group. It's a finite Coxeter group. This means it's generated by reflections.
Sorry, I missed
Yeah.
it. So this spinning, which kind of data is it? So every group has this thing?
No, reductive groups actually, for a reductive, you can classify reductive groups in terms of pin root data, so-called.
Okay, can I have different pinnings of the same group?
Yes, you can. Yes, of course. You can, there is always a dual one.
Okay, cool.
So anyway, so you can have different pinnings of the same group. And in fact, we will, anyway, I was not going to make this point, but since you asked, whatever we do, you can actually change these pinnings by some square of a unit in the field. And then, you get the same thing. So anyway, so this is a finite Coxeter group in the, generated by reflections. So the so-called simple reflections corresponding to these roots in delta, which is a finite set. So corresponding to alphas in delta, and so any element can be written as a word of S alphas, and so there is a well-defined length function from this while group to natural numbers, and a unique longest element. Okay, so let L be the length of this longest element, and then this Bruha decomposition gives a cellular structure on G in the following sense. So it's a filtration of G by open subsets. So so let me write it in this. It has exactly L steps. So L is the length of the longest word, and so this is so-called a big cell. This has this kind of a formula. So okay, I need to explain something. So whatever the Borel, whatever that special subgroup is, which was fixed above, so you take this W naught, which is the longest element in the while group. When I put a dot above, it means you choose a lift to the normalizer of the torus. So then you can see that as an element of G, and then you take B W naught B, and then this is the omega 0. So the so-called big cell, it's an open set, and yeah, so you can explicitly write down what the stata are. So the stata are precisely disjoint union of the so-called Bruha cells. So these are a disjoint union of elements of the form BWB, where W varies over words of length L minus I. Okay, so now, so this BWB have a special structure. So these are, okay, so let me write that down real quick. So, okay, maybe okay, so I'll just say that BWB is an A1 fibration, or yeah, okay, let me write that AN fibration over WT. So, well, I mean, so this Borel actually appears as, I mean, as a scheme is isomorphic to the torus times some affine space. So what the explicit form of the affine space, I'm kind of suppressing at this point. People who want to know can ask me later. And then this BWB is an A1, so it's, I mean, A1 homotopically, it's as good as WT, and I mean, that is as good as T. Now, when you have this kind of a filtration, there is a standard way of writing down a chain complex, which in low degrees will compute the homology that you want, and so that is this cellular chain complex. Is yeah. And yeah, so you basically do what topologists do. So you take the homology of omega I modulo omega I minus 1 in degree I, and then it maps to hi minus 1 at the next level. So the differentials are kind of defined canonically, in the sense that so this factors as okay, so now you can look at the cofiber sequence for the inclusion of omega I minus 1 inside omega I, with the cofiber being this quotient. And you can look at the long exact sequence of homology, and then this map will be the connecting map in that. And then if you look at the same thing at the next level, this will be the natural map in that. And the way this is defined, it's clear that this is a complex. And of course, this is an object that we don't understand, but all the computations in some sense work because of the motivic, the so-called motivic homotopy purity theorem of Morel and Vygotsky, which tells us that if you look at the ith term of this cellular A1 chain complex, well, okay. So for any regular embedding, so the motivic homotopy purity theorem says that the cofiber is the Thom space of the normal bundle of this inclusion. And now using yeah, so using well, okay, the Quillen-Suslin theorem, so to speak, you can check that the normal bundle is actually trivial. So then what you will have is the Thom space of the trivial bundle on this omega t, and that's going to have a very specific form. And when you take this homology, so the indices are kind of I mean, they are kind of arranged, or luckily get arranged in a way that this happens to be exactly the homology group that we know, and the only homology group that we know. So in fact, okay, anyway, so I'm not going to write all this down. I'm only going to write down the final conclusion, because I want to show how to do computations with it. So of course, this is the direct sum. This is going to be the direct sum over ki min of it tensor h naught of wt. So that's what pops out at the end of the day. And yeah, so this is the complex, and this is I mean, this is a complex we understand. The hard part is, I mean, at least the terms of it we understand, because I mean, this is abstractly so okay, this part over here is usually written as ZA1 T, or let me remember this W, because this is the so-called free strictly A1 invariant sheaf on the torus. And so, I mean, this is kind of, so to speak, of state type, in the sense that, well, this is just, I mean, ZA1 of something of this type. And there's a standard decomposition of this, and one knows how to study this. So now, I mean, we have a complex of which consists essentially of Milnor-Witt K groups of the Milnor-Witt sheaves, and then I mean, it's about determining what the differentials are and then making computations. So okay, so let me quickly mention a special case, so which will be important. So here's a special case. So that is that of G equal to SL2. So in this case, one can compute everything by hand very explicitly. So in this case, this while group is Z mod 2, and it's generated by a simple reflection. And so this reflection corresponds to a root. And I mean, there is a co-root that is associated to it, which I'm going to use, but it happens to be the identity map. So the T, I mean, here T is actually isomorphic to GM because it's a rank 1 torus, but I'm keeping it T just to clarify how the complex really looks like. Yes, yes.
There's a
please.
question which asks
Yeah.
whether your complex depends on orientations.
Yes, very much so. The complex, I mean, the cohomology doesn't, of course, but the differentials are very much dependent upon the choice of trivializations. And I mean, when you choose different trivializations, you need to carefully keep track of how identifications are changing. Yeah. So yeah. In fact, yeah. Well, it's kind of unfortunately added 20 pages to our paper, but yeah. But anyway, it's essential. Anyway, I'll come to the. I'll show. I want to show at least one explicit computation. But anyway, I hope I succeed in the last 15 plus epsilon minutes. But anyway, so the. Yeah. So this. Complex, I mean, okay, so now I have not nicely explained it, but let me just tell you how it looks like. So this has just two terms. So the zeroth term is, so is this kind of a funny object, and then the first term is K1 Milnor-Witt tensor ZA1 of T. Okay, now how do these look like explicitly? So this is just ZA1 of GM. So this is, it splits off Z, so it's pointed at 1, and then ZGM. But this guy is just K1 Milnor-Witt. Okay, and similarly, this guy is isomorphic to again Z direct sum ZGM. Okay, so now, okay, how does this, so one can check by hands that this differential is given as follows. So note that this K1 over here is also a free strictly A1 invariant sheaf on GM. So this is this one. And so now this thing has an inclusion inside ZA1 of GM cross T, or GM cross GM actually, but yeah. And you can go into ZA1 of T cross T by this co-root, which I mentioned, which happens to be the identity map in this case. But I mean, this is the same computation in the general case, which is why I'm writing this in this weird way. And now you can look at the multiplication map from T cross T to T. And then there is an explicit isomorphism between these two. Okay, so maybe let me not use an equal to sign. So this is precisely given by the multiplication of S, and yeah. So this is how the complex comes. And now if you actually compute what the differentials are, so of course this thing. So when I write tensor, is the tensor in the category of strictly even invariant sheaves. So this thing on the right is basically K1 Minovit. Okay. Okay, let me write in this fashion. It's K2 Minovit, direct some K1 Minovit. So basically, when you tensor K1 Milnovit with Z, you get K1, and when you tensor this K1 Milnovit with this copy of K1 Milnovit, you get K2 Milnovit, and then this goes to K1 Milnovit. There's some Z, and you can check that this this matrix is exactly given by. I mean, this map is given by this matrix. So it's the multiplication of eta from K2 to K1 and the identity over here, and the rest components are all 0. So I mean, of course, so this computation immediately shows you that the 0th homology at so of course the homology of this I'll call cellular homology, but the 0th homology is Z, which is untouched over here, and then the first homology is K2 Milnovit. This is just a little sanity check. So this was already proved by Fabien in his book, that this is how the H1 of SL2 looks like. Okay, so now let me come to the precise version of the main theorem, and I was hoping to give a proof, but yeah, anyway, I'll hurry up. So okay, so it's going to involve some group theoretic details, which I'm going to give, and I'm also going to outline the proof. Yeah, I mean, whatever, I mean, however much I can in this time. So, okay, so I have not really explained this, but any any group with, I mean, with the properties that we have is classified by a Dinkin diagram, and then these have, I mean, these have some, yeah, so roots, and then they have certain lengths, but the so okay, it follows from I mean, one can find this in Bourbaki, for instance, that the lengths of different roots can only be of two types. Either all of them are of the same length, or some of them are short and the others are long. So there are maximum two types of lengths. So so you pick any long root, and so then I mean yeah, so as I told you, there are these root groups U alpha and U minus alpha. So in case of SL2, these are the upper triangular and the lower triangular matrices with one on the diagonal. So if you take the group generated by these two the so-called root groups, this is actually isomorphic to SL2 under hypothesis. So then the theorem actually says that the inclusion of this root group into G induces an epimorphism so on the cellular homology of S alpha to. So of course there are several natural questions that one can ask. Is there functoriality and so on and so forth? So of course, if the filtrations are compatible, then there is functoriality and so on. But yeah, okay, anyway, so this is where our K2 Milnovit comes from. And then the statement says that if G is of symplectic type, then phi is an isomorphism. And if G is not of symplectic type, then phi induces, so it factors through modulo eta and induces an isomorphism. So so from K2 Milnovit to K2 Milner, and then yeah, so this is phi, and then this is the isomorphism that you have. Okay, so now, okay, let me finally come to the sketch of this. Okay, so how should one compute this? So of course we have, we have the cellular chain complex. So this is the relevant part of the cellular chain complex that we have. Okay, let me just call this, yeah, so let me call this del1. So let me, as usual, write Z1 of G as kernel of del1. And then you have, so this is what we have to determine. So this H1 is the quotient of this, of Z1 by the image of the del2. And so the first observation, which is that G is A1 connected under our hypothesis, implies that so the torus action on G so induces an action of the free strictly A1 invariant sheaf on the cellular homology, and so this action is trivial. And so you can go modulo this T action, which actually simplifies your work quite a bit. So this yields an exact sequence. So we are going to tensor over this ZA1T by Z. So that's just quotienting by ZA1T. But this right-hand side remains the same because the action is trivial. And now, so we have to explicitly determine this map, but we note that we are working in the category of strictly A1 invariant sheaves. So the advantage of this cellular chain complex is that the terms are strictly A1 invariant. So what you can do is you can so it suffices to dualize and determine. So yeah, so the idea is to dualize and determine. So the morphisms, so the homomorphisms in AB A1K from H1 cell G, M. So this is going to be the kernel of the map between the duals. To yeah, so the homs from the term on the left to M for an arbitrary M. And now if you so if we can show that so if this is equal to the M minus 2 of K, or eta torsion in the M minus 2 of K, twice contracted M on K, then we are done. Okay, so that's the idea. So you, the computation is done dually, and yeah. So the only thing is that you have to do this for an arbitrary M. And okay, so at this point, how much time do I exactly have? Because now, yeah, now it becomes important. Do I have like 5 minutes?
Yeah, you have 5 minutes. Sure.
Okay, so okay, let me try to write down the main parts, and then of course those who are interested can ask me for details later. Okay, so now first we have to determine the kernel, and then we have to determine the image of the previous differential. So the degree 1 differential is kind of easy to determine. from what I wrote in the case of SL2. So I'm not going to explain everything in detail for, again, the reasons of time. So this will be the direct sum of copies as many as the rank of G from K1 Milner bit. So okay, so recall that so this is over so this should be the direct sum over words of length L minus 1. And so it can be checked that these are precisely of the form W naught times SI. And so then you take these guys, and that's what it is. And then it goes into the zeroth part, which is CA1 of W dot of T. Okay, so now this one has to read it off. I mean, it's at each stage it is quite parallel to the SL2 case, but I'm just going to write this informally how this looks like. So this. So okay, so K1 is the free strictly even invariant sheaf on GM, K1 Milner weight. So given a unit, you can tell where the unit goes, and this defines a unique map from K1 Milner weight. So this is something that I will keep on using again and again. And so if you take this, and then if you take the so-called unit element over here, so then this goes to so now there's a slightly tricky formula which is of this form. So I'm writing it in this way because one, I mean, of course, one identifies this with say, for instance, ZA1 of T, but we really need to keep track of this guy. So I'm writing it in the form where it appears as this guy times some element from T. So that's how it should be really read. But anyway, so it's a little technical. I don't want to go into the details, but this I mean, so any element of T will give you an element of this ZA1 with square brackets, and then I mean, one has to I mean, this is a pointed sheaf, so one has to, I mean, really keep track of what one is doing. And then in fact, it's going to be like, so this by definition is this symbol minus 1. So yeah, anyway, don't ask me right now why, because it's anyway. So that's the point. And then of course determining the kernel is a bit I mean, it takes a little bit of work, but one can do that. And it's fairly elementary to determine the kernel, which is which happens to have the following nice formula. So it's the sum of certain copies of K2 Milner width, and then certain copies of K2 Milner. So that's the form that it has, and so basically this I is, so this part, so there's one copy of K2 Milner width for every simple root. And yeah, so okay, I don't know how to give a justification for this, but this is basically going to keep track of what happens, I mean, from the previous stage. I mean, it has something to do with that, but anyway, I'll not say more about this. It's a bit confusing and complicated. So okay, so that's how this Z1 looks like. So how does C2 cell look like? So this guy is just the direct sum over length L minus 2 words of something of this form, K2 Milner width tensor ZA1 of WT. And so of course now one has to be careful about how many of these are. So so let n be the number of words of length L minus 2, and let R be the rank of G. That means it's also the rank of the torus. And in that case, then you have this explicit formula for what we want to determine. So okay, not an explicit formula. I mean, I have not described the map yet, But yeah, so this is what we were trying to compute, and this was the dual of I mean this thing over here. So let me just write it out in detail. So it's the kernel of the following map. So the map is between so when you map k to Milnovit to M, you get the twice contraction of M evaluated at k, the rank many copies, and then some copies of eta torsion. And so these are over I less than j. So these are r minus 1 by 2 in number. And then this maps to m minus 2 n copies. So these are the number of direct summands in this sum over here. So let me now describe this map. So the description actually depends upon the intrinsic combinatorics of this root datum, and it has something to do with the Cartan matrix. And if you look at the Cartan matrices of symplectic type and non-symplectic type groups, you will know where the dichotomy comes from. So let me try to explain, although I have kind of like I've gone out of time, so I'm going to take a minute extra, but I'm sorry about that. So let me very quickly try to say what this map is. So an element on the left hand side over here will look like a bunch of xi's from these copies and a bunch of yij's for I less than j. And so then this map sends it to, so let me write zij. Well, okay, because this, I mean, I'm writing ij in square brackets because I mean, it depends upon how many of those are. So now this map is given explicitly as follows. So if alpha I and alpha j are not adjacent in the Dynkin diagram, so then this guy is just minus of yij. And so if alpha I and alpha j are adjacent, then so this zij, it looks as follows. So it has this yij plus an error term, so which is some unit times some nij epsilon. So I'm going to explain what this is, times xj. So for some unit, by unit I mean something in the field, and by this symbol I mean the corresponding symbol in the Grothendieck ring. So this symbol actually okay, so this symbol actually is inside GWK, and this nij is the so-called entry in the Cartan matrix, which is the inner product of alpha j and alpha I check, whatever this is. But I mean, what one should know is that this is always 1, 2, or 3. Yeah, I think I need a minus sign over here, but anyway, so it doesn't matter. So when I put a sub epsilon over here, this just means the corresponding integer in the Grothendieck ring. So it's either the hyperbolic form or just 1. Okay, so I mean that's kind of easy to see, and I don't unfortunately have time to explain. So now once you know this map, you have to, it's just about solving some equations, and one trick that allows you to to make this computation is that this GWK action on eta torsion is trivial. So what do I mean by this? So this happens because when you have a unit like this actually corresponds to an element of this form in the Grothendieck ring. So I think those who are familiar with the Brylinski theory would know this. And then if you multiply this to something which is in eta torsion, this part won't contribute. So it's just like the action of 1. So that is what makes the computation simpler, and one can explicitly compute it and then get the result. So I'm sorry for going over time, but this is kind of the proof in a nutshell. But yeah, it's a little technical. So there are other ways of computing and proving this, which should hopefully appear in a sequel. But I'll talk about this, yeah, some other time. I'm sorry for going over time, and thanks for your attention.
Thanks a lot for your talk. Let's thank Anand.
Thanks.
And please ask questions if you have any.
In your example of SL2, did you mention that K1 minoid tensor with itself is K2 minoid?
Yeah, because it's tensor in the A1 sense.
Tensor over Z, right?
No. It's tensor in AB A1. So the way to see this is that K1 is the free strictly A1 invariant sheaf on GM, and K2 is the free strictly A1 invariant sheaf on GM smash GM.
Okay.
So that's how it comes.
Is it correct that Km minoid tensor Kn is Km plus n?
Yeah, the tensor in this sense.
Okay.
Yes, that is true.
So how do I understand this tensor product? Is tensor product over Z then sheafify?
No. So I don't know. This is actually, I think all this is there in chapter 2 or 3 of Fabien Morel's book on A1 algebraic topology. So where he, shows that, Kn Milnovit is the free strictly A1 invariant sheaf on GM smash n times in the reduced sense.
Okay, I see.
And then, yeah, by using these observations, you can get it.
Thank you.
So what do you do in the sequel? If you could say.
So we so of course this is difficult because the differentials are just extremely painful to compute. So all this, so that's because G is kind of complicated. So what you do is, if you work with G mod B, then the differentials have an easy form, much easier form. So well, okay, just to okay. Okay, this is how the cellular chain complex of G looks like. But if you look at the cellular complex for G mod B, then these terms will just not appear. And actually, if you look at the formula for differentials, the terms that involve these are really kind of painful to handle. So one can, it becomes considerably easier to write down differentials, but it's still a little complicated because you have to really painstakingly keep track of trivializations that you use. So this, well, anyway, so what we do is we compute the full cellular homology of G mod B, first of all, and then there is another proof of this result, a very short one, using the results for G mod B and some spectral sequence calculations. So you can actually write down natural spectral sequences connecting G mod B and G. You can write down a Rothenberg-Steenrod style spectral sequence or a Serre type of spectral sequence, and so on. So these two kind of agree in very low degree terms, but not in general. And you can use this to, you can also use this to get these kind of results. But this proof is kind of just from first principles, in the sense that it doesn't use any kind of non-trivial result about algebraic groups, only all that is present in Bourbaki. But but the other proof actually uses the, one can give a proof using Demazur's determination of Chow ring of G mod B and so on. But anyway, those things one can do, but the point is to compute the full cellular homology of G mod B. So there were already results about this over in the world of topology over real numbers, from the point of view of Morse homology and also infinitesimal representation theory. You can get quadratic enrichments of all these results. So that is one part, and anyway, I think I haven't talked about this stuff, but there's also the strict A1 homology, which one believes is kind of more. Yeah, but anyway, that is, yeah, we don't know how much we'll get there.
Cool stuff.
Sorry, I have one more question further to my previous one. So the free strictly A1 invariant sheaf Z A1 functor, so it will change smash product to tensor product, right?
Yes, yes. So in fact, yeah, yes.
Okay. So this free functor is defined over arbitrary scheme.
I mean, as far as I know, only over a perfect field as of now. I mean, all the ingredients are. I mean, so there are a lot of in. Okay, how? Well, I mean, the proof crucially depends upon the connectivity theorem, the unstable A1 connectivity theorem, which we don't know if it works over a general base.
But yeah, I mean, yeah, over perfect field, it can be applied to any scheme, right?
Over perfect field, it is fine. Over a perfect field, it is okay. And yeah, I mean, now over even finite fields, it's okay. I mean, earlier, all those results were only for infinite perfect fields, but I don't know about imperfect fields either.
Okay, thank you. That's great.
So, yeah.
Hmm.
But anyway, I mean, any results about algebraic groups can be, I mean, you can talk about them over an arbitrary field because, I mean, luckily split, I mean, reductive groups are defined over Z. They are actually defined over spec Z. So by using some formal stuff, you can actually, I mean, if your schemes are defined over spec Z, then you can do some things I mean, depending upon the situation.
Are there any more questions? If not, let's thank Anand again.
Thank you all for listening.
So I'm a bit let me stop recording.